Welcome to the 3D structure of alkanes. Today, we're exploring the world of stereochemistry. On left side, we see the standard 2D structural formula for ethane, C2H6. It's laid out in a basic grid: carbon atoms in the center, hydrogen atoms branching off at rigid right angles. Just single bonds and saturated carbons, right? They look flat on paper. And it's true. When we draw them in a textbook, molecules look like static, two-dimensional blueprints. But now, look at the right side. This is the reality. Instead of flat lines, we see a dynamic, glowing ball and stick model. Luminous green and blue arcs swirl around the carbon-carbon bonds, showing motion blur as the atoms spin. The quote at the bottom reveals the truth, but in the real world, molecules aren't flat. They twist, they turn. Understanding this dance is the secret to understanding how molecules actually behave. Because those single bonds act like axles. The atoms attached to them are in constant motion, rotating and shifting into different 3D shapes. This constant twisting, this stereochemical structure, is exactly what determines how a molecule interacts, reacts, and exists in our physical world. Let's see the basics of hybridization and geometry. At the center of our display, we have a carbon atom marked with a C bonded to 4 surrounding hydrogen atoms. But we aren't looking at simple, flat lines. Notice the glowing, green, teardrop-shaped lobes connecting them. These are not standard atomic orbitals, they are called sp3 hybrid orbitals. How are these formed? Look at the diagrams on the periphery. Carbon doesn't just use its basic, unmixed orbitals to bond. Instead, it takes 1 spherical 2s orbital and 3 dumbbell-shaped 2p orbitals and mathematically blends them together. The result of this mixing is 4 identical sp3 hybrid orbitals, perfectly optimized for bonding. Because these 4 orbitals are filled with negatively charged electrons, they naturally repel each other. To find stability, they push away from one another until they are as far apart as physically possible in 3-dimensional space. This mutual repulsion forces the orbitals to point toward the 4 corners of a triangular pyramid. As indicated at the bottom of the screen, this specific 3D arrangement is known as tetrahedral molecular geometry. And because of this perfect, symmetrical spacing, the angle between any 2 adjacent bonds is precisely 109.5 degrees. This specific geometry dictates how molecules fit together, react, and function. Welcome to Module 3: Ethane and the Newman projection. To truly understand how molecules behave, we have to look at them from the right angle. On the top left, we have the sawhorse view of an ethane molecule. But imagine physically moving your perspective to look straight down that central carbon-carbon bond. This perspective gives us the Newman projection. The front carbon is represented as a simple intersection of 3 lines, a Y shape. The back carbon is the larger circle behind it, with its own 3 hydrogen bonds poking out along the edges. Flattening the 3D structure this way makes it incredibly easy to track the rotational relationship between the front and back atoms. As that central carbon-carbon bond rotates, the molecule cycles through 2 extremes. First is the staggered conformation. Here, the hydrogens on the front and back carbons are perfectly offset, maximizing the distance between them. This results in minimal hydrogen-hydrogen repulsion. It is the molecule's happy state, the configuration with the lowest possible energy, but as the molecule continues to spin, the front and back hydrogens eventually align directly over one another. This is the eclipse conformation. The negatively charged electron clouds of these overlapping hydrogens fiercely repel each other, creating intense torsional strain. Because of this internal friction, it is a much higher energy, unstable state. We can map this entire rotation on a potential energy graph. As the torsion angle changes from 0 to 360 degrees, the molecule's energy peaks during the eclipse states and bottoms out during the staggered states. The energy difference between these peaks and valleys is about 12 kilojoules per mole. Now, at room temperature, there is more than enough ambient thermal energy to overcome that 12 kilojoule hurdle. The ethane molecule isn't locked in place. It is constantly spinning like a tiny propeller. However, because nature always favors the path of least resistance, the the molecule prefers to spend the vast majority of its time hanging out in those stable, staggered valleys. Welcome to Module 4, Butane and the concept of steric hindrance. We are stepping up our complexity. Instead of ethane's 2 carbons, butane has a chain of 4. Imagine positioning your viewpoint to look straight down the central axis, the bond between carbon 2 and carbon 3. As the text warns us, the extra bulky methyl groups on the ends of the chain, carbon 1 and carbon 4, are about to cause some structural drama. Let's track the rotation around that central bond. First is the anti-conformation. Look at the Newman projection. The 2 large CH3 methyl groups are positioned diametrically opposed, a full 180 degrees apart. Because they have maximum spatial distance, there is no crowding. As indicated by the green energy wave below, this is the lowest energy, most stable state of the molecule. But as the molecule twists, those groups get closer. In the gauche conformation, the methyl groups are now 60 degrees apart. Notice the glowing orange arrows. The electron clouds of these large, bulky groups are starting to physically bump into each other. This physical crowding is called steric strain, and it pushes the molecule into an intermediate energy state. As rotation continues, we reach the standard eclipse conformation. Here, a large methyl group perfectly overlaps with a smaller hydrogen atom. This forced alignment creates an intermediate energy penalty. Finally, the rotation forces the 2 massive methyl groups directly over top of one another 0 degrees apart. This is the fully eclipse conformation. The intense physical clash and electron repulsion between these 2 bulky groups result in the highest possible steric strain. Consequently, this is the highest energy, most unstable configuration the molecule can experience. In the real world, as butane twists and turns through these shapes, it constantly battles this steric hindrance, naturally preferring to spend its time resting in the spacious, low-energy anti-conformation. We will see the Remming modules in next video. If you found this helpful, don't forget to like and subscribe for more deep dives into the molecular world. See you in next video. Happy learning chemistry with Harshada.